So whenever we use a composite scale, we always ask this question: how can we be sure that we are measuring something? How can we be sure that this whole bunch of questions is measuring a single construct? Why do we even need many questions? Well, the answer is because our measurement is different from measurement in physics. Of course, if you are measuring something like length, it's just enough for you to place a ruler once and you can see here is length. But if you are measuring a subjective phenomenon, first of all, this ruler is invisible and it's kind of flexible. It changes from moment to moment, just like this tattooed ruler on an arm. So this estimate will be very imprecise, very unreliable. And also, sometimes we measure fairly complex constructs, which are impossible to formulate just using one question. For example, extroversion. Of course, you can ask a question, are you extroverted? But if a person is not a psychologist, they will hardly understand you. As a result, you need to ask them at least maybe 10 questions, asking like, are you ambitious? Do you like talking? Do you like loud music or parties and things like that? All those things that make extroverts so appealing. And then you take together all those 10 questions and you calculate an overall score of extroversion. But you cannot really say that each of those questions reflects extroversion because none of them captures extroversion as a whole. And because our ruler is so bad, we can measure many times to improve the quality of our measurement. Why does it happen? Because every result of our measurement is always a random variable. So imagine I'm asking you a question, are you a happy person on a scale from 0 to 10? And you have some kind of level of happiness, maybe 7, which does not really change with time, which is kind of your maybe baseline characteristic. But at one moment you might give me an answer like 7 or 8 or 6, and sometimes more rarely you can even say 10, or you can even maybe say 4. So your individual answers at every moment or to every item will always be distributed around your true score, but will not be equal to this true score every time. So our observed score is basically a combination of our true score and some kind of random error, some kind of differences from moment to moment that kind of bias our measurement. As a result, our measurement is almost never trustworthy enough, is almost never precise enough. But if you repeat this measurement many times and you average the results, the true score will remain the same, but random error will be different at every trial. And if you average, it will cancel itself out. As a result, your measurement will be fairly precise. So that's the logic of composite scales when we ask many questions to obtain a more precise measurement. And then people ask, why do you psychologists always ask so many questions? Well, because I want to measure your individual difference precisely and not just as sociologists do, because sociologists don't really care much about individuals. So many people have tried to come up with those composite scales that would be comfortable to use, that would be good from a scientific point of view, but unfortunately they did not work. Guttman tried to create a bunch of items arranged in such a way that agreement with each subsequent one kind of implies the agreement with previous ones, just like this social distance scale. But unfortunately, in practice, this has too many issues, too many assumptions, and sometimes it's even impossible to get such a set of items. So this Guttman's idea was kind of abandoned, even in the intelligence domain. Another guy who proposed his attempt was Thurstone, who said, let's formulate a bunch of questions and let's ask expert judges to rate each question in terms of how strongly it reflects the construct. And then when people give answers, we will just use expert ratings to determine the position of this person on the scale. But unfortunately, also it did not work. The only type of scale that worked and that remained in history was Likert scale. Don't call him Likert because he was Francis Likert, an American sociologist who proposed this idea. Let's just take a bunch of response items called Likert type items or Likert items, and let's just calculate the sum score as the mean or as a sum of all answers to those individual items. As a result, we'll get a better measurement. Of course, this scale has also some problems. The unit of measurement is not clear. There is no absolute zero, for example, because this scale goes from 1 to 5. And even if there was a zero, it would not be clear that it would correspond to a zero amount of property being measured. But nevertheless, this scale became the basis for subsequent psychometric theorizing, and it is in application to Likert scales that classical test theory was developed. And now we'll take a look a little bit at the definition of reliability in classical test theory. What is reliability? Reliability is defined as the proportion of variance associated with the target construct in the observed test score. So if you remember, our test score is basically a bunch of individual differences, and it is comprised to some extent by true differences in the construct that is being measured, the variance that is associated with individual differences in intelligence, for example, and the variance that is associated with random error, because people got distracted or people were more motivated at some point. So this random error will always be present. And reliability is the proportion of true score in the test score, the proportion of the target construct in the test score. And you can imagine two opposite situations. Because it's a proportion, it ranges from 0 to 1. So if your reliability is 0, it means that the result of your measurement is a complete mess. It is absolutely random. You just randomly assigned people to some scores. But if your reliability is 1, it is also a very implausible situation when there is no error at all. Your measurement is infinitely precise, which almost never happens. So we always want reliability which is closer to 1, but of course it might be impossible to attain. Classical test theory makes some assumptions. Some assumptions that are not quite always tenable. In addition to the main equation that observed score is a sum of true score variance and random error, another assumption is error is completely random. On average, error is 0, and its standard deviation is called standard error of measurement. And we will come to the standard error of measurement very soon. But the assumption is that error is normally distributed, which might not always be the case. Another assumption is that true score is not associated with error. So basically, the precision of measurement in the center of the scale and on the ends of the scale is equal, which is also not quite the case. And finally, the fourth assumption is that errors of individual items are not associated, which is also not quite the case, because if you have two items that share some strange word that some people fail to recognize, their reactions to those items will be biased in a similar way, so there will be a covariance of errors or correlation of errors. But nevertheless, despite these assumptions do not perfectly hold in all questionnaires, we still use classical test theory as a basis for estimation of reliability. So because our observed score is basically some kind of variance, reliability is the proportion of true score variance in observed score variance, or 1 minus the proportion of error in observed score variance, because observed score is true score plus error. Basically, it's very easy to see how this simple formula comes up. And how can we estimate reliability? Basically, true score does not change. And as a result, you can use different approaches. You can measure the same construct at different times, for example. And then you assume that true score does not change, but error is random. And if you calculate correlation between the first time and the second time, this correlation will reflect the proportion of true score, or square of correlation, but we'll come to that very soon. Another approach is to use two different test forms, like two parallel forms that measure the same property but with different tasks or with different questions, and you calculate the correlation. And again, true score is supposed to be distributed across individuals in the same way, whereas random error will be random. So the higher is your correlation, the higher is your reliability. Or you can use reliability as consistency of answers to different items, or internal consistency of a test. And this approach is used most often. And of course, if you have a bunch of experts rating something, a bunch of judges or observers, you can also calculate the consistency of their answers. And it's a good idea to evaluate reliability of expert ratings, even though we don't often do it. But reliability of expert ratings is just as important as reliability of a test, because experts might not be very reliable in how they evaluate whatever it is that they evaluate. So how can we quantify reliability? In order to do it, we can use a very simple coefficient, which was proposed by Lee-Cronbach. Before Lee-Cronbach, people would just take a test, split it into two halves, and correlate the scores obtained using the first half and the second half of the test. But this was a very bad idea, because depending on how you split the test, the result will be always different. And Cronbach came up with this formula of alpha coefficient, which is basically an average reliability for all possible ways to split your test in two halves. There are two different formulae that you can use, but they are absolutely equivalent. The difference between the results is usually 0.001. It's very, very small. The first formula is easier to understand, alpha standardized. It depends on two things: K, the number of items in scale, and R, average correlation across all pairs of items. So if you want to increase your reliability, you either need to make more questions in your scale, or you need to make those questions more similar, so that average correlation is higher. And as a result, you can obtain the same reliability with like 4 questions that are very similar, and with 20 questions, but that are all kind of different. So depending on the construct which you are trying to measure, it may be hard to get questions that are all similar. Like, for example, for extraversion, those behavioral expressions of extraversion are fairly different. As a result, for personality, you usually have large questionnaires. But for things like emotions, maybe sometimes 2 or 3 questions is enough to capture an emotion, such as happiness, for example. There are, of course, some issues with alpha, because sometimes it tends to underestimate reliability, and rarely it may overestimate, but usually it's a lower bound estimate. So true reliability might be a little bit higher. And why is alpha so important? Because depending on alpha, the precision of our test changes. The higher is our alpha, the more precise is our test. And precision of our test is quantified by this statistic, which is called standard error of measurement. Last time we discussed standard error of the mean. Why is it called standard? Because it is kind of expected. And standard error of the mean, if you remember, is the expected standard deviation in a sample of estimates of the same mean score from independent samples. So basically, in different samples of the same size, you measure something, you calculate mean, and the average will be probably close to the population mean, but the standard deviation across those measurements might be very large or might be very small if you have large samples. Pretty much the same thing with standard error of measurement. If you have a sample of individuals, for each individual, their observed test score is their true score and some kind of random error. For John, maybe their test score equals their true score, and for Sally, maybe their test score is 2 standard deviations away from her true score. Who knows? So you can say that on average, this deviation is 0, because on average, random error is 0. But what is the deviation, standard deviation of this distribution? How large are on average those differences between the true score and the test score across the whole sample of individuals, or across repeated measurements of the same individual? So this standard error of measurement depends on reliability. It is very easy to calculate it. Basically, you need to take Sx, which is standard deviation of our observed test score. We calculate standard deviation in a sample, and we multiply it by a square root of 1 minus reliability. As a result, we get standard error of measurement expressed in raw score test points. And if we depict this graphically, we can see that actually this distribution, this function has a slightly nonlinear shape because it's basically a square root. As our reliability increases from 0.7 or 0.8, the increase in precision happens increasingly quickly. So the question is, how large reliability do we really want in order to attain sufficient precision for our purposes? Unfortunately, there is no single answer. Imagine that we are doing an IQ test and we have 2 children, John and Sally. John's IQ is 105 and Sally's IQ is 115. And we remember that for IQ, mean score is 100 and standard deviation is 15. So basically, John's IQ score is very close to the middle of this normal distribution, whereas Sally's IQ score is exactly 1 standard deviation above the mean, which means that approximately 1 in 6 children is as smart as Sally. And the teacher, based on this measurement, may say, okay, maybe Sally needs to go to a special class for gifted children, and maybe John needs to stay in the regular class for regular children, because she trusts the results of this IQ test. But when the teacher makes this conclusion, she makes the assumption that test score equals true score, which may not be the case. Of course, this assumption is very intuitive. If we measure temperature with a thermometer which we stick under our arm, our true temperature is almost equal to the temperature reflected by the thermometer. This error is very, very small, so we pretend that it does not exist. But with a psychological test, the true score is almost never equal to the test score. So in order to find out the limits in which the true score is supposed to lie, we can only assume that test score is somewhere in the center of this distribution, and we can calculate confidence interval for an individual true score. And if you remember, 95% of all measurements are within 2 standard deviations from the mean. And standard deviation for independent measurements of the same individual is called standard error of measurement. So in order to create a confidence interval for this IQ scale, first we need to calculate standard error of measurement. Imagine that reliability of our IQ test is 0.75. Standard error of measurement will be square root from 0.25, will be 0.5 standard deviations, and standard deviation is 15, so it will be 7.5 IQ points. Which means that we can take John's score and we can calculate confidence interval as his true score plus or minus 2 standard errors from the test score. As a result, the confidence interval for John's true IQ is 90 to 120, fairly large. There is a chance that John is also gifted. And for Sally, 95% confidence interval is 100 to 130. So there is kind of a 50% chance that Sally is gifted, or 50% chance that Sally is kind of in the average range. And if you plot those two normal distributions on one graph, you can see that they overlap. And there is actually a 25% probability that John's true IQ is actually higher than Sally's. And you can do the same calculation for a different Cronbach's alpha. So for example, if Cronbach's alpha would be 0.95, these confidence intervals would be much smaller, and the chance of making this error would be only 7%. So we could trust this test, actually. But when the reliability is as low and the chances of this error are as high, we can ask the question, for this important decision, such as placing a child into a different class which might determine their future life, is this precision of measurement enough? And the answer is maybe, maybe not. How large should our reliability be? That's a good question. So if you want to calculate reliability and to practice a little bit with some psychological tests, you can basically take a look at this subjective happiness scale, which has only four questions, and you can try answering those questions right now by putting this video on pause. And once you did it, you can calculate your total score. You need to add up your scores to questions 1, 2, and 3, and add 8 and subtract your answer to question 4. Because your answer to question 4, you need to flip around. Instead of 1, 2, 3, 4, 5, 6, 7, you need to change it to a scale 7, 6, 5, 4, 3, 2, 1. Because the first 3 questions measure happiness and the fourth one measures unhappiness. And this is called a reverse scored or reverse coded item. So you need to add up your answers to the first 3 items, then add 8 and subtract the fourth item. And if you have data from a bunch of people, you can calculate this in SPSS, and you can easily evaluate reliability. So for this subjective happiness scale, the scale of Sony Lubomirsky, the evaluation of Cronbach's alpha based on variances is 0.89. Based on standardized items, based on correlations, it is also 0.89. So it's a fairly reliable scale. But if we'll take a look at individual items, we have this table which reflects how alpha would change if we delete each item. We would see that if we delete the fourth item, which is reverse coded, alpha would not really suffer, and it might even increase to some extent, which suggests that maybe this fourth item is not needed. But we need to be very careful about deleting items to improve alpha in this way, because this fourth item might be very important to represent the construct of happiness. And if we just look at the alpha and remove items blindly based on statistics, we can end up with a scale that is extremely narrow in terms of how much construct content it captures. So the mean score here is 19.7 and standard deviation is 4.88. And you can use this range, mean plus minus 1 standard deviation, to determine the average score range. So if your score is between 15 and 24, it means that you probably have an average score. But if your score is like below 15, it's low. If above 24, it's high. And you can also calculate standard error of measurement very easily, because you know standard deviation and you know alpha. And standard error of measurement will be fairly low. But if your score is, for example, 23, and you fall in the medium range, still based on the standard error, you can say that there is a very high probability that you can actually be a very happy person. So how much probability is enough? It depends on what kind of test we have and in what situation we apply, whether the decisions that we are making are very important. For high-stakes tests, usually we aim for a reliability of 0.95. And tests like IELTS or SAT That's their reliability values. They are usually above 0.95. For clinical measures, something like 0.90, which you use to decide whether a person should walk away or be hospitalized. For personality measures, where we just give feedback to people, it can be somewhat lower, like 0.80. But if reliability is lower than that, it's really better not to use this questionnaire to give individual feedback, because there is a high chance of making a mistake. For research measures, most reviewers and most people would say that like 0.70 is acceptable reliability, but there is no lower bound. If you are not making conclusions about individuals, especially if you are kind of averaging this score across large groups like countries, even if your reliability is 0.3, this might be fine. For example, for Hofstadter scales, reliability is very, very low. They are not suitable to make conclusions about individuals, but they are very useful to make conclusions about countries, because if we average across 1,000 individuals from a country, we get a very precise estimate, even though for individuals this estimate is a complete mess. So this was a little bit about classical test theory. It is still used in most cases to develop psychometric tests. Of course, people know that there are some problems with classical test theory. It makes some realistic assumptions that each question reflects the construct equally well. So when we just add up answers to different questions, we end up with a score that maybe is slightly less precise than it would be if we took into account how well each question reflects the construct. And also it assumes that all error is random, which is not always the case. In principle, if you apply a very, very complicated factor model to scale your scores, you will get a more precise estimate of individual differences, but it will correlate with a simple sum of answers at about 0.96, 0.97 or so. That was my experience. So for research, it really does not matter. But if you are interested in very precisely estimating individual differences, very important tests like SAT, Russian ЕГЭ, and other high-stakes tests, they are usually developed based on item response theory. It is a more contemporary alternative to classical test theory, which allows to estimate different parameters of each item. And based on these estimates, you can actually create much more efficient tests. First of all, you can make sure that error is equal across all ability ranges, or you can select subsets of items that are optimal for respondents with low, medium, or high ability range. And as a result, you can get equally precise estimates, but also you can save a lot of time, because you can give some questions to measure ability approximately, and then the following questions can be tailored to the ability range in which a person is found to be. And this is called computer adaptive testing, because it typically requires computers, but it can save a lot of time. Instead of administering 100 tasks to all individuals, regardless of their range of ability, you can give like 10 questions or 15 questions tailored to this particular ability range, and it will be just as precise. Unfortunately, in research, it's rarely used, IRT, for some historical reasons, and because it's so demanding in terms of computation and in terms of sample. You need a few thousand of individuals. So in our research, we typically use either classical test theory, or we use confirmatory factor analysis, which is also a similar thing as IRT, but slightly different. And whenever you encounter a questionnaire, you need to at least know its Cronbach's alpha. Of course, in the last 10 years, there have been quite a few publications showing that Cronbach's alpha is not perfect, and there are better estimates, like greater lower bound reliability, which is better for asymmetrical items. Or if you conduct some kind of factor analytic model, you can use Omega, McDonald's Omega. Usually your reliability estimates will be slightly higher, but maybe not drastically higher. So most people still go on using Cronbach's alpha, even though everyone knows its limitations, but most people still go on using it because it's so simple. It doesn't require a model. You can basically calculate it for any bunch of items, and it's available in SPSS. Maybe the most important reason. So whenever you encounter a questionnaire or you develop your own, you always need to calculate your Cronbach's alpha. Of course, there are also some philosophical limitations, like all of this only makes sense if you measure something that is quantitative. And some psychometricians argued that you actually need to prove this assumption first. Otherwise, you may arrive at a bunch of questions which measures what they call a semantic artifact. But most research psychologists pretend that they never heard this, and we just go on creating scales without much consideration for the nature of the thing that we are measuring. And calculating Cronbach's alpha applies to a bunch of no matter what items.